Welcome to Building TechTalk. I'm your host, Matt Stewart, and I'm here with Dr. Doug Brown, our resident expert. And we are going to be getting into a really interesting conversation that we had with Stephen Harpur of Progressive Planet. And in order to get the most out of that conversation, we wanted to take a little bit of time, a little bit of a prequel here, in order to set the stage for this conversation so that everyone is kind of up to speed on why this is so important. We're going to be talking about the cement industry and the incredible opportunity there is to have a drastic impact on reducing the carbon emissions worldwide from this industry. And that's all the work that Stephen Harpur is doing with his company and all the R&D. But in order to get the most out of that conversation, Doug, we want to talk about a few things just to get everybody up to speed and set the stage. So I'm going to turn it over to you and take it away.
Yeah, absolutely. Thanks, Matt. Yeah, so this is an industry that's kind of near and dear to my heart. And it's one of those sort of materials, cement and concrete, that's almost so ubiquitous that it's become invisible. And if you want to put into context the size of this industry, every year we consume about 4 tons of cement per person. If you put that into context, that is a massive emitter. Cement is a heavy carbon emitter. And just to fact check a little bit about what you're about to hear. So the cement industry last year contributed about 6 to 8% globally to the CO2 emissions that were human made. In China, that number is a bit higher, and they're the major consumer of cement now. That's about 12%. So when we're talking about small impacts in the carbon footprint of this industry, it has potentially huge ramifications for countries trying to meet their climate accord goals. Steve Harpur spoke very eloquently about the cement industry, and I'm not going to go too much into the chemistry behind it, but I just wanted to clarify some of the topics that we discussed so that the viewers have a bit of context as to what they're hearing. So rheology is a term that came up over and over, and it's just really looking at the flowability of the cement and how conventional cement behaves that we're used to working with, and trying to match it with new materials that are being added and introduced to it. And so zeolite, which you're about to hear about, is one of these major sort of initiatives to look at replacing fly ash in cement. And fly ash is probably not something that comes up in sort of general conversations, but it usually is about 30% by weight, the material that you find in sort of modern cement. And it's simply because it's cheap, it's widely available, and people are used to working with it, and it behaves very well in cement. Fly ash is a byproduct of the coal industry, and as we start to move towards hitting some of our climate goals, we know that coal is going to be one of those sort of target industries to be phased out. And so the cement industry is looking at a basic shortage globally of this sort of byproduct. And if you think about 30% of 4 tons per person per year, there are not that many industries that produce byproducts that can fill that void. So one of the new materials that they're looking at is this zeolite. And zeolite has a whole bunch of unique properties, but it does have the potential to take over this sort of 30% component of cement. But in investigating that potential, you have to address a whole bunch of concerns. Cement is one of those foundational sort of building materials. And so companies like Steve that are looking at not only producing a new material, but doing the science behind it to prove it to the industry, like, hey, we have a solution. I mean, this is like exciting stuff.
Because we're talking about, you throw out the numbers about how much of an emitter that industry is. I mean, that makes it maybe somewhere in the range of the 4th largest country. If it was a country, it would be like behind China, India, and the US. Is that?
Absolutely.
Probably? Okay. So yeah. We're talking about taking one of those and doing what can't be done really in a modern society, which is slash their carbon emissions by, say, 40%.
Yes.
That can't really be done, or not today, but we're on the brink of potentially being able to do that with new additives to the cement. Is that correct?
Correct. Yeah.
Is there anything else we need to level up to make sure everyone's on the same page before we jump into this really interesting conversation?
One more thing I'd just like to clarify too is the conversation around silica. So silica is this sort of controversial component of building materials because when you don't fully appreciate the science behind what you're discussing, it can kind of make you be a little bit worrisome about it. So silica is found, it's one of the most common elements on Earth, but in its sort of pure form, or purer form, as both its crystalline and amorphous structure, it has sort of different properties. And so silica has been sort of associated with silicosis, which is when you inhale this dust, either chronically or acutely, it can start to cause respiratory issues that are not really curable. And that is based around crystalline silica because it's not biocompatible with us. Amorphous silica doesn't have those same health issues. It's not good to breathe in rock dust, but it doesn't cause necessarily silicosis. And so materials like fly ash, which have a large sort of silica content and have potentially both of these structures within them, it's kind of unique when you talk about cement, because cement has accepted fly ash, which potentially has this issue because it's contained within the cement structure and it's not sort of environmentally available. But in the pure forms of the raw materials, this is something that really needs to be considered. And so that's something that needs to be addressed whenever you're looking at something that contains silica, which will come up in this conversation.
Okay, so now we understand silica, we understand the industry and what the industry is looking for out of this product. So now we're going to turn it over to our on-site interview at Progressive Planet with Stephen Harpur. All right, guys, welcome to Building TechTalk. We are on location today, which is really exciting.
Road trip
To BC, British Columbia, Canada. We're just outside of Vernon. We're at Progressive Planet's, let me say, am I saying this right? A zeolite processing facility?
We're at Progressive Planet's rock comminution facility.
Rock comminution facility. I learned a new word today.
So comminution is the pulverizing of rocks into powders.
Excellent. So we are here with Stephen Harpur, not that Stephen Harpur, the Stephen Harpur of Progressive Planet, CEO. And we have our resident experts, as always, Dr. Doug Brown and Scott Jenkins of ZS2 Technologies. And we're here in, like we said, in Vernon, and we're all being very responsible. Since we are traveling between provinces, we are wearing our COVID-19 masks, and hopefully everyone can hear okay. We are also on an industrial site, so there's going to be a little bit of background noise just for our audio listeners. That may be a little bit of something you have to listen through. Some lovely trucks going by right now. But today we're here to talk about zeolite and all the great things that it does. And so it's what goes with the theme of our podcast, which is new ideas, new technology, new science within the building industry. And Stephen, we want to start with you for Progressive Planet and the company. Just can you give us a little bit of background? Where did it come from? Why does it exist?
So Progressive Planet has a tagline, solutions for a livable planet. And essentially our core mission is to produce materials that are consumed in a modern society in a more sustainable way. Our flagship product that is rapidly being developed for commercialization is a blend of pulverized zeolite and pulverized glass, hence comminution. So this facility that you can see behind us is our first comminution facility where we plan to pulverize zeolite and glass in a blend with some proprietary additives to produce a superior product for the construction industry to compete against using fly ash for the same purpose. Fly ash is horrible from a sustainability perspective because it's a byproduct of burning coal to produce electricity. And zeolite, unlike fly ash or Portland cement, doesn't require any heating to be effective as a 20% replacement for either fly ash or Portland cement in ready-mix cement mixes.
Okay, so let's just back up a little bit as far as you're talking about the fly ash and the zeolite as an additive. So we're talking about cement. We're talking about concrete here as far as a building material and making it better. Is that
absolutely? Right? And I'd really like to talk about the carbon footprint of Portland cement. The number one consumed material in the world is fresh water. The second consumed material in the world is ready-mix concrete. And there's a difference between concrete and cement. Cement is the glue that holds concrete together, and concrete is a combination of cement, water, sand, and aggregate. And this glue, Portland cement, which holds concrete together, it's made from limestone. And limestone has a chemical equation of CaCO3, 1 calcium atom, 1 carbon atom, and 3 oxygen atoms. So CaCO3 equals calcium carbonate or limestone. In order for this limestone to behave as a glue, it has to go through a chemical change. And that change happens through heat. So when you heat up calcium carbonate or limestone to 1,000 degrees Celsius, it goes through a phase change where 44% of the rock off gases as CO2. The chemical equation is CaCO3 plus 1,000 degrees Celsius equals CaO, or calcium oxide, which is the main component of cement, and CO2, which is a gas that the more CO2 we have in the air, the more it contributes to global warming, trapping heat on the earth. So in what we have found, and this is not new technology, the Romans figured it out over 2,000 years ago, and they were able to replace a portion of their cement with a pozzolanic, or pozzolanic, I should say, material, and this is a volcanic ash. And there are various forms of pozzolanic materials in the world. Some are made by nature, and some are made by humankind. In nature, we have volcanic ash, and the secret here is that silica, which is the main component of most rocks, is a crystalline structure. And as a crystalline structure, it's not reactive with cement. However, when silica is rapidly cooled after it's heated, it doesn't have time to reform its crystalline structure, and we would refer to that as amorphous silica. And amorphous silica is highly reactive when you take 20% of your Portland cement out of a mix and replace it with amorphous silica. So zeolite, pumice, there are other forms of volcanic ash, and these are all amorphous silica. And we have a permitted mine in Cache Creek where we mine amorphous silica in the form of zeolite.
So I'm going to jump in here to simplify things. And what was interesting for us as we've gotten to know Stephen and his team and the company that he's building with Progressive Planet, and really these two guys, as they talk chemistry and talk shop and talk above my head at, much higher levels. What was interesting to me is learning that it's estimated 10 to 12% of the world's CO2 production is coming from the cement industry. And I think, Doug, you've said it best in terms of for investors, where the business and industry is going, is that right now the energy industry is kind of in the crosshairs of a lot of people, but on deck is the cement industry. And Progressive Planet and Stephen and what they're doing is coming up with materials, proprietary processes to significantly reduce the CO2 and energy embodiment in traditional Portland cement production. Would that be correct?
That's
sort
fair.
of the simple way to say we have a much more sustainable, natural product, the zeolite, that actually has even stronger performance parameters. I think, from my learnings, right? It's a better material.
Yeah, and I'm happy to speak about that. Now, Scott talked about Doug, who's got a PhD in chemistry, and I've got high school chemistry. However, we felt that we needed Scott to improve the general good looks at the table. So that's why he's in the middle.
My mother says I have a face for radio. Let's be honest.
So I'd like to add to when we talk about amorphous silica occurring in nature, generally you find it in nature as volcanic ash. So heated silica, rapidly cooled, did not have a chance to reform its crystalline structure. There are multiple ways that humankind also produces amorphous silica. The first one is fly ash. And when we consume or combust thermal coal to produce electricity, the soot that goes up the flue is electrostatically collected, and this is high in silica content. Again, it rapidly cools and doesn't have a chance to reform its crystal structure, so we have amorphous silica in the form of fly ash. The problem with fly ash is that it has an awful carbon footprint because we're burning coal to make electricity. The second way that humankind produces amorphous silica is in the production of steel. When you're producing steel, you take iron ore and you heat it up, but that ore also contains silica, and the steel slag, again, heated up and rapidly cooled, doesn't have a chance to reform its crystalline structure. So steel slag is a great pozzolanic material that can replace 20% of Portland cement in a mix. And then finally, one that you may never think of, but glass. So glass is made predominantly 80 to 90% silica. It's heated up, it's rapidly cooled, and I've read a statistic that 76% of post-consumer glass is used once and then goes to landfill. So your pickle jar, your beet jar, all of these things at the supermarket, once they go and they're disposed and they go to landfill, we're spending enormous amounts of energy to heat this material, make it amorphous silica, and then use it once. That's crazy. So we started experimenting, and if you pulverize glass down to a very small particle size, it works fantastic as a pozzolan to replace, again, 20% of Portland cement in a mix. So our proprietary mix, and we've actually applied for a trademark under the name Sequester. C is the symbol for carbon in the periodic table. So we are looking to use the name Sequester for our new material we want to bring to market. And it's a little bit of a play on words, but it's actually what we're trying to do, and that is to sequester carbon. One of the attributes of pozzolanic concrete is that it keeps getting harder over time. And as it cures, it absorbs CO2 from the atmosphere. So it does sequester carbon dioxide. The best known source of pozzolanic, or best known structure made of pozzolanic concrete, is the Pantheon in Rome. And the Pantheon is
no reinforcements, right?
No reinforcements, 1950 years old, no rebar, still standing strong today.
Oh, that's fantastic. Yeah. One thing I just wanted to touch on, maybe that you hadn't mentioned, is the importance of silica being amorphous. So crystalline silica causes silicosis, which is an extremely bad disease where you basically have silica that is crystalline, and if you inhale it, it cannot be processed by the body, and it causes something called silicosis. So when he's talking about amorphous silica, he's basically saying that silica is not harmful to humans in that way. So which is an important distinction.
Health attribute.
Yeah.
From what we're talking much healthier and much more sustainable, but higher performance materials through chemistry.
Very much so. Again, on the carbon footprint, it's not just the fact that 44% of the weight of the main ingredient in Portland cement off-gases, but you have to heat it in two phases. In the first phase, you have to heat it to about 1,000 degrees. And then after you have the off-gassing of the CO2, the second phase, you heat it up to 1,450, and you add iron, silica, and alumina, and then that material is finished its processing at 1,450 degrees, and then this material that comes out of the kiln is finely ground to produce Portland cement. So by heating this material all the way up to 1,450 degrees, tremendous amounts of hydrocarbons are burned, once again releasing massive amounts of CO2 into the atmosphere. And about 6 months ago, several large investment fund managers who collectively represent about $42 trillion, I believe, and I have to check my facts here, but I believe it's 42 trillion in funds managed wrote letters to the 5 largest cement companies in the world and said, you have to change your practices or we will not invest in you. So there is a very strong push to make the production of Portland cement more sustainable.
And is that something that's widely known by the average person of how carbon intense or how energy intensive it is to make cement? I think most people, the most interaction they'll have with ready mix concrete is buying a bag at Home Depot, mixing it up in a wheelbarrow and tossing it in a fence post or something like that. And it just seems like crushed rock. It doesn't seem like, and you're mixing it with water, that don't see everything that goes into it to actually get it to that powdered state and that ready mix state. So is this something you're finding when you go talk to people about what you do or why you're doing it? Are they surprised that this is something that could have such a dramatic impact on CO2 emissions?
I think that as a whole, the public is not aware, but it's slowly the awareness is coming. And I take an analogy of smoking. I'm 51 years old. When I was a teenager, it was cool to smoke. And after decades of education, it's no longer cool to smoke for teenagers. And then we saw recycling. And at first, when we had household recycling, there were a lot of skeptics and people were unwilling to do it. Now there's a general acceptance. We are at the very early stages of public awareness of the carbon intensity of the production of Portland cement. People are generally aware that automobiles are not great, and they talk about cow methane emissions, and the public certainly, in my conversations, I would hear those two topics discussed. And part of my mission is to make the public aware of just how much CO2 is generated in the production of Portland cement. There is no other one activity that I could personally be involved in where a greater impact could be made because the fact of ready-mix concrete being the second most consumed material in the world.
So, Steve, you bring up a good point. And one of, our sort of mitigation strategies with CO2 is sort of to avoid some of these, larger emitters or products. Do you see sort of a shift coming that may move us away from materials like concretes towards things that may be classified as more sustainable, like wood-based structures?
I don't believe that concrete will be consumed less. In fact, if you look at market studies, the consumption of concrete will increase. We just need to do it in a more sustainable way. We are also starting some work on the production of geopolymer cements, and they don't consume any Portland in their mixes. So, and there are other companies that are doing tremendous work in this area. We're certainly not the only company, and we are making strides with respect to creating that lower footprint.
Let me add one thing. I've learned a lot from Stephen and obviously from Doug in this arena in terms of how the carbon footprint can be not just reduced, significantly reduced here with some of your technologies and the better materials. But also there's a chance, and it goes back to some of your experience and your early work with carbon engineering when you were there and completing your PhD, is could we potentially even go a step further with this massive industry and sequester carbon? Could it actually become not just neutral, but could it be carbon negative? And there is that potential, and maybe you guys could each touch on that a little bit. That there's further science and work that you're working on now that could take this to a whole other level.
Well, I have a chip on my shoulder with Doug with respect to this because he stole my carbon pressure vessel from my lab yesterday and said he'd like to borrow it, and I'm not sure I'll ever get it back.
Well, he stole a 3-wood of mine once. Thank you for that. I'm not getting that back.
So we actually we did some work where we created a pozzolanic mix with our Z1 zeolite and then cured it in a pressurized vehicle with 100% CO2. And then we could measure the amount of CO2 by an increase in weight in the cylinders that were in the curing chamber. And again, there are other companies doing this, but pozzolanic concrete absorbs CO2 over time, and it continues to get hard for a very long time. And we just had a press release this morning where we announced results of the compressive strength, and we had a target of 30 MPa at 28 days with some cylinders that were curing at University of Alberta. And at the 56-day interval where we were going to do another crush based on COVID, they were not allowed into their lab, and we didn't get to crush those cylinders until 98 days. And at 98 days, those cylinders had compressive strength between 37 and 41 MPa.
Wow, that's impressive. Yeah.
Can we quantify that a little bit as far as an increase? Is that?
Yeah, that'd be about 30 to 40% higher strength efficiency, Steve. Would that be fair to say?
So you're going to put me on the spot, but 7 divided by 30 or 11 divided by 30 would be your increase in strength from 28 days to 98 days.
I was hoping somebody at the table is better at math than I am. So
don't look at me.
Either way,
don't look at me.
That is a significant, and that's purely just from sitting and curing, and it sounds like absorbing CO2 during that time.
Yes. So the CO2 does convert to a
carbonate.
A carbonate. Sorry,
Yep.
Doug, I was lost for words, but I got rescued by the PhD in chemistry. Thank
all
you,
good.
Dr. Doug Brown.
More
I
than a
should
pretty
like
face.
to. I also, my 5-year-old, we socially distanced at our farm yesterday, and my 5-year-old decided that his name was Dr. Doug Brown.
Dr. Dougie Doug.
Yeah.
That's like you're the triple D.
That's right.
The triple D. One thing, I know as we're getting close to the end of this podcast, and Stephen, thank you so much for hosting us
Yes,
here
thank
in
you.
Beautiful British Columbia, but at the facility. It's kind of neat to be on site. But you can see why this is actually so exciting. We're in this facility here. They're producing the product right now. They're doing all the testing. You're bringing more materials in. You can bring your strategic partners in. This is a huge opportunity for the world. In the second most consumed, you started off our podcast with that, the second most consumed product or material on the planet next to water.
Well, and really, if
Yeah.
you're talking about, I think, Scott, you threw out a number that anywhere from 8 to 10% or more of the world's CO2 emissions come from cement production. I mean, even having that or a third of that would be more than shutting down Canada completely.
Correct.
And not emitting a single thing out of this country. So the work you guys are doing to transform the cement industry is phenomenal. Have you seen, as far as adoption of this technology that you've come out with, what kind of response have you gotten from the cement industry?
So the cement industry wants to see the data. So we now have compression tests. There are 5 other tests that we are doing, either CSA or ASTM certifications. Again, the press release where we did a shareholder update this morning, August 14th, it listed the 5 tests. So industry wants to know that this material is durable. They want to know in a freeze-thaw cycle of a Canadian winter that it won't disintegrate. They want to know that if you use this in acidic soils, that it won't deteriorate. And we call that sulfate resistance testing. They want to know that when you add the rocks or the aggregate, that you don't get an alkali silica reaction. And so we're doing alkali silica testing. And of course, they want to know the compressive strength. And then one of the critical things with respect to concrete is what air voids are in it. So there's an air void analysis test that we will also do. So it needs to be chemically resistant. It needs to work in the wintertime. It needs to have compressive strength, and it needs to have the right air voids in the concrete. So we are going to be completing this testing with the University of Alberta. The longest of these tests is a sulfate resistance, which is about an 8-month test. We tested sulfate resistance with superb results using just the Z1 Zeolite, but we haven't done the test with the Z1 blended with post-consumer glass. So that's what we are embarking on over the next 8 months.
That's fantastic, Steve. And if I could touch on the concrete industry just briefly as well, having personally been in it for a few years, there is an extreme global shortage in the fly ash market, particularly as sort of societies begin to phase out coal.
And the cement industry is in a position now where they need to look at alternatives. And zeolite is leading the pack, it would be fair to say, is one of the most promising alternatives to replace fly ash on this sort of global scale. So it's really good to hear that your company may have all the data to support its replacement here in the near future, because I know that coal in North America here, over the next 50 years might not be there, and fly ash in many regards is 30% or more of the concrete mix. So what are we going to do?
And you're also almost negating the benefits of having it as a carbon sink. If you're producing that much carbon to get your fly ash, it's almost a zero-sum game there, instead of having all the benefits of just the straight zeolite. So
yes, I have some final words with respect to that. There is an ability to quantify the difference in the carbon footprint of producing Portland and producing a pozzolanic replacement for a portion of Portland. And we anticipate in the next year that we will hire an engineering firm to make that quantification. And we've actually received proposals from third-party firms looking to do this and then to sell carbon credits based on the difference. And we're not quite there yet, but that is in our near future to quantify the difference.
sounds like we're going to have a return episode to check in and see where we're at.
It's a great idea.
Great idea.
All right. Thank you, gentlemen. We're going to wrap up this episode of Building Tech Talk. Thanks for listening, everyone. And remember to subscribe either on YouTube, hit that subscribe button, or we are now available on Apple Podcasts. Just search Building Tech Talk, one word, and subscribe on Apple Podcasts. Thanks a lot, gentlemen.
Thanks, Stephen.
Thanks, Stephen.